In the previous lessons, we analyzed the energy and environmental impact of data centers, focusing on the techniques adopted by computational infrastructure providers to reduce consumption and emissions. The perspective was that of those who manage the data center, an actor who can intervene on the hardware, on load distribution, and on application scheduling to improve overall efficiency. However, in this view, applications are treated as black boxes. The infrastructure provider has no visibility into the internal logic of the software, nor into how it was designed and developed. They can only analyze its behavior in terms of resource usage and execution patterns, and adopt general strategies to best manage the application's execution. In this lesson, we change perspective and see why developers also play a key role in software sustainability, and how their choices can significantly influence the energy consumption of applications. In this context, the concept of green software emerges, recognizing that the decisions made during the design and development of code also have a direct impact on the energy efficiency of applications. The approaches that aim to improve the energy efficiency and environmental impact of software start from the observation that relying solely on infrastructure optimization is not enough. Sustainability must be considered from the very earliest stages of the software lifecycle, from defining the architecture to writing the code, all the way through to maintenance and the evolution of the application. Integrating environmental criteria into technical decisions can significantly help reduce consumption and improve performance, making software an active part of the transition toward more sustainable IT. In this lesson, we will focus on the developer's perspective and look at the main factors that influence the environmental impact of software. The quality of the code directly affects the amount of computational resources required to run an application. Inefficient algorithms, suboptimal data structures, or redundant loops can lead to excessive use of computational resources, increasing energy consumption. Writing clean, well-structured, and high-performing code is not just a good software engineering practice, it is also a choice that has environmental implications. Optimizing more demanding processes, avoiding redundant calculations, and favoring less computationally expensive operations are all strategies that help reduce the software's impact. Another key aspect is related to the choice of application architecture, such as the number of components, communication patterns, or the adoption of microservices versus a monolithic architecture, which influence the system's complexity and the way it uses resources. An excessively fragmented architecture can generate communication overhead between services, inefficient network usage, and higher latency, resulting in increased consumption. At the same time, microservices generally offer a more energy-efficient application architecture compared to monolithic designs, promoting a more efficient use of computational resources. However, designing efficient software should not focus solely on aspects related to its execution, but rather on its entire lifecycle. Sustainable software is also easy to update, monitor, and maintain. Excessive complexity, poor modularity, or lack of documentation can make maintenance more costly in terms of time and resources, with indirect impacts also from an energy perspective. Moreover, software that requires frequent updates can cause unnecessary cycles of compilation, testing, and release. Carefully designing the software lifecycle allows for waste reduction, extending the product's lifespan, and improving the overall efficiency of the development process. The way an application collects, processes, stores, and transmits data has a significant environmental impact. Processing large volumes of data, if not strictly necessary, results in high usage of CPU, RAM, network, and storage. For example, overly verbose logs, indiscriminate data collection, or excessive use of streaming can generate avoidable energy costs. It is therefore essential to design software so that it handles only truly useful data, using filtering, compression, and caching techniques, and minimizing unnecessary traffic and requests. Many modern applications rely on libraries, frameworks, and external services that can introduce inefficiencies that are difficult to control. Heavy, outdated, or poorly performing dependencies can significantly increase loading times, memory usage, or the number of required operations. Furthermore, some libraries include unnecessary features that are still loaded and executed. Therefore, the conscious choice of lightweight, modular, and efficient dependencies is crucial to limiting the environmental impact of software. The ways in which the application is executed and scaled affect the amount of resources activated and the duration for which they remain active. An application that does not release unused resources, does not shut down when idle, or scales excessively can cause disproportionate use of the infrastructure. Implementing intelligent autoscaling mechanisms, idle state management, and shutting down unused components is essential to reduce consumption during periods of low load and to dynamically adapt to actual demand. Another aspect that impacts application efficiency is the choice of programming language. A 2017 study compared various programming languages and their efficiency in performing a set of tasks, highlighting significant differences between different languages. Languages such as C, Rust, and C++ rank among the most efficient, both in terms of execution speed and energy consumption. In contrast, interpreted languages like Python, Ruby, and Perl consume up to 59 times more energy than the most efficient one. More recent studies confirm this trend even for artificial intelligence applications. C++ and Java are substantially more efficient than Python, with the latter being up to 54 times less efficient in training and inference. These observations run counter to the popularity of these languages. Referring to the TIOB index, which measures the popularity of programming languages, Python is by far the most widely used language, with a 10% increase in popularity compared to the previous year, followed by languages like C, C++, and Java. However, it is essential to balance sustainability and productivity. In many contexts, the ease of use of languages like Python can justify their energy cost, provided that the implementation is optimized. The most important initiative for promoting software sustainability to date is the Green Software Foundation, or GSF. It is a global initiative created with the goal of defining shared standards for software sustainability, metrics for measuring the energy consumption and environmental impact of software, and a set of best practices or green software patterns that support design and implementation practices to promote sustainability. The main metric proposed by the Green Software Foundation is the Software Carbon Intensity, or SCI. Software carbon intensity measures the carbon emissions attributable to an application in relation to its functional unit. It takes into account the energy used to run the software, the source of that energy, and the number of instances executed, such as users served or tasks completed. The metric considers both the emissions resulting from running the software and those from the manufacturing of the hardware on which the software is executed. The Green Software Foundation also proposes a Green Software Patterns Catalog, which describes the main design practices supporting software sustainability classified according to the type of application. Some of the suggested practices include profiling software performance to identify energy bottlenecks, not just performance ones, minimizing computational load by removing non-essential or infrequent processing, reducing client-side processing when possible, especially on mobile devices with limited battery, limiting the data transmitted between client and server by optimizing APIs and payloads, and designing with dynamic scalability in mind to avoid having unused active resources. Practices for improving software energy efficiency do not replace initiatives aimed at enhancing data centers, but rather complement more traditional approaches to optimizing the use of infrastructure resources. To make software sustainable, it is necessary to define shared standards and to consider not only the execution phase, but the entire life cycle.